Hello, welcome to my talk on understanding and calculating the atmospheric pressure. Atmospheric pressure is much more complicated than the pressure in water. In this talk, I will make a short introduction on the historic views on understanding the atmospheric pressure. And then I will make a discussion whether we can do a direct integration for getting the atmospheric pressure. And then I will move to gas equation and atmospheric temperature, and the discussion on the atmospheric pressure, the formulations, and the comparisons with the references. In the last, I will give an example for the air buoyancy, a hot air balloon. In the history, there were some important events for people to understand the atmospheric pressure. Here, the first example is the Torricelli's vacuum experiment in 1643. In the experiment, Torricelli filled a long smoke tube with mercury, and then he put the tube upside down and the opening to the ball of mercury. And we can see the mercury in the tube will lower to certain height. Here, H is 760 millimeter Hg. And based on this height of the mercury, we can calculate the atmospheric pressure, P0, given as this. So it is 101,325 pascals. Here, rho m is the mercury density. It is 13,595 kg per cubic meter. In this experiment, Torricelli provided a way for measuring the atmospheric pressure. And another important phenomenon in this experiment is the creation of the vacuum on the top of the small tube here. Another important event was the Mandelbrot hemispheres experiment. See this drawing. So we can see two hemispheres of a diameter about 0.5 meter were held together by removing the air inside. Thus, a force of about 20,000 Newton was applied to the hemisphere. And in the experiment, 16 horses, 8 horses on each side, but they couldn't separate the hemispheres. If we want to calculate the force acting on the hemisphere, we can calculate in this way. The projected area of the sphere would be given as S equaling to this. So it is 0.196 square meter. And the force to hold the hemisphere together, if we assume the vacuum is created in the sphere, so the force would be calculated as pressure times the projected area. So it is 19,860 Newton, very close to 20,000 Newton. And now we can see some modern performance of the Mandelbrot hemispheric experiment. The picture took in 2015. Now we are going to calculate the static pressure in the air. The pressure equation is very similar to the static pressure in water. The difference is the density here. Rho air is the air density. We know at sea level, the air density is about 1.225 kg per cubic meter. If we take the coordinate z pointing vertically up. So one question is, can we have a direct integration given by this, as we have seen in the calculation of the static pressure in water. Superficially, this expression makes sense because the pressure in the atmosphere would decrease when the altitude Z increases. But in fact, this direct integration might be only acceptable when Z is in a small range. For instance, within tens meters, where the air density can be regarded as constant, and this direct integration would be correct. But if we apply this pressure calculation for the atmospheric pressure, it could result in some incorrect conclusions. The first one would be at the height Z1 equaling to 8,434 meters, the pressure would reach the absolute zero. However, if we compare this height with the Everest, which is at 8,848 meters high above sea level, obviously there is no vacuum on the Everest or elective pressure there. It should be noted, elective absolute pressure is impossible in physics. And also, most passenger airplanes fly at an altitude between 11 to 13 kilometers above the sea level, and in that height, there must be air for flying airplanes. Then we may ask, what's wrong with the calculation? Now we look back at the pressure differential equation in the atmosphere given as this. So our question would be, is this equation correct? The answer for this question is yes, because the pressure differential equation is derived based on the correct physics, so it is always correct. The problem in the direct integration is with the density of air, because it is not a constant, but a function of the altitude Z. Although the gravitational acceleration g can be generally regarded as a constant for most applications. We see some facts here. In the atmosphere, a large change of the air density can be seen with the altitude. It can change dramatically with the altitude and the temperature as well. And within the maximum height of the Earth's atmosphere, up to Z equaling to 100 kilometers, the Kármán line, where the gravitational acceleration can have only 3% change when compared the gravitational acceleration on Earth. Therefore, the gravitational acceleration g can be generally taken as a constant. The correct calculation for the atmospheric pressure should be made by employing the gas equation, and the air can be well approximated as an ideal gas. The gas equation would be given by P equaling rho air times Rs and T. The atmospheric density rho air, Rs is the specific gas constant given as this, T is the absolute temperature, and P is the atmospheric pressure. In fact, we can use this gas equation to calculate the pressure P0 at sea level, given as this. Here, the air density at sea level would be 1.225, and the Rs is the gas constant. Temperature, we take 15 degrees So it is 288.15 K. The result would be 101,327 pascals, only 2 pascals different from the value we used before. So from this gas equation, we can obtain the air density expressed as this and consider the pressure differential equation. These 2 equations together, we can obtain the equation for the pressure given as this. Now we look at the equation, we can see these 2 parameters, the gravitational acceleration g and the specific gas constant Rs, are both constant, but the T, the absolute temperature, can be a function of Z. So we can see the atmospheric temperature would be important in the calculation of the atmospheric pressure. Now in this slide, we can see the temperature changes with the altitude. Generally, we have 4 different atmospheres below the common line at 100 kilometers above the sea level. The common line is the upper border of the Earth's atmosphere. So here we have troposphere, which is from 0 to 11 kilometers above the Earth. And above the troposphere, we have stratosphere, which is from 11 kilometers to 50 kilometers. And above that, we have mesosphere, which covers the height from 50 to 80 kilometers. And on the top of the Earth's atmosphere, it is thermosphere, from 80 kilometers to 100 kilometers. And we can see in different spheres, the temperatures would vary different with the altitude. In the troposphere, it decreases linearly from 15 degrees to here, and in the stratosphere, the temperature either is constant or increase linearly with the altitude. And then in the mesosphere, the temperature dropped, and in the thermosphere, temperature increase again. Because of the complicated relation between the temperature and the altitude, we need to calculate the atmospheric pressure in different layers. The first layer is in the troposphere. We can see the temperature is decreased from 15 degrees Celsius at sea level linearly to minus 56.5 degrees Celsius at the altitude of 11 kilometers. Therefore, we can have an expression for T as a function of Z given as this. We substitute this relation into the revised air pressure equation. We could have the differential equation for the atmospheric pressure in the troposphere given as this. And here we can see G and Rs are the constant. So we can integrate this equation. Therefore, we could obtain the pressure expression as this. Here, P0 is the atmospheric pressure at the sea level, and Z is the altitude from the Earth's surface in meters. So if we calculate the pressure, we can find that it is very close to the reference value, the red line here. We will see how this value is calculated later on in this talk. And based on the gas equation, we can calculate the air density. It would give the expression as this. So here, rho 0 is the air density at the sea level. It is 1.225 kg per cubic meter. So here, The important value would be at the top board of troposphere, Z1 equaling to 11 kilometers. There, the pressure P1 would be 22,633 pascals. It is about 22.3% of the pressure at sea level. And the density there, rho 1 would be 0.364 kg per cubic meter. It is about 29.7% of the air density at the sea level. We will use this value if we go on to calculate the air pressure and the density. Here, I will show how we can calculate the pressure and the density in the stratosphere. And for illustration, we only consider the first part of the stratosphere from 11 kilometers to 20 kilometers. And in this layer, the temperature is constant at minus 56.5 degrees Celsius. So using the differential equation, we have the expression for the pressure in the stratosphere given as this. Here, in this layer, the first part of the stratosphere, all these three parameters would be constant. Therefore, we can integrate this differential equation directly. We have this. And then we apply Z1, P1. We could obtain the pressure in the first part of the stratosphere given as this. Here, Z and Z1 are in kilometers. Similarly, if we know the expression for the pressure and we apply the gas equation, we could obtain the air density expression at the first part of the stratosphere at Z between 11 to 20 kilometers, given as this. And if we need to go on to calculate the atmospheric pressure and density, the board at Z2 equaling to 20 kilometers, the pressure P2 would be 5,474.5 pascals. This pressure is about 5.4% of the pressure at the sea level. And the density rho 2 is 0.088 kilogram per meters cubic. It is 7.18% of the density on the Earth's surface. We take the example for the Concorde, which flies at height Z equaling to 18 kilometers, where the pressure would be 7,504 pascals. It is 7.4% of the pressure on the Earth's surface. Density rho would be 0.1207 kg per cubic meter. It is less than 10% of the air density on the Earth's surface. Now in the next two slides, the reference formula for the atmospheric pressure and the density will be given. See here, the atmospheric pressure would be calculated using two different formulations. One is for the temperature lapse rate, LB, is not zero. P is calculated using this formula. And when the temperature lapse rate, LB, is zero, we calculate the pressure using this formula. And we can see the temperature lapse rate would be dependent on the altitude. See here, when the altitude is from 0 to 11, the temperature lapse rate would be minus 0.0065. And from 11 kilometers to 20 kilometers, the temperature lapse rate would be 0. This actually means when LB is 0, that means the temperature would be a constant in the layer. And when the temperature lapse rate is negative, that means the temperature would decrease. And when LB is larger than 0, for example, from the altitude 20 to 32 kilometers, LB would be 0.001, and so on. All this formula for the atmospheric pressure available for the atmosphere up to 80 kilometers. Similarly, for the density, we have the similar formulation. 1 is for LB is not 0, and 1 is for LB is 0. So this temperature lapse rate would be the same as that before. Now in this slide, the atmospheric pressure and density will be compared for the reference formula and the formula we got in this talk. So the red line is from the reference, and the square from the formulas in this talk. So we can see the atmospheric pressure calculated very close to the reference. Similarly, for the air density, the formulas in this talk give the very close result to the reference value. And from this two drawing, we can see on the Everest at the height 8,848 meters, the pressure would be about 31% of the pressure at the sea level. Density would be about 39% of the density at the sea level. If the flight altitude is taken at 13 kilometers, the pressure would be about 16%, and the density is about 22%. In the next few slides, an example for a hot air balloon is examined. The question is, a hot air balloon with an inflated diameter of 10 meters has a total weight of 500 kilograms. This including the weight of the hot air inside the balloon. The question is to find its upward acceleration at sea level at the instant the restraining ropes are released. The second question is the maximum altitude the hot air balloon can achieve. In here, we assume that the variation of the density in the troposphere is given by this. This is the same as the formula we presented in the previous slide. Here, Z is the altitude in m, and rho is the density in kg per meter cubic. In the solution, at sea level, where Z0 is 0 and the rho is 1.225 kg meters cubic, and we assume the air density change across the balloon is ignored because the small distance. For the question A, we calculate the volume of the inflated balloon is given as V equaling to 4 divided by 3 pi r cubic. So this would be 523.6 cubic meters. According to the density at the sea level, so the buoyancy force at the sea level would be given as B0 equaling to rho 0 G times V. That would be 6,290 Newton. And therefore, the net upward force at the sea level would be given by F equaling to the buoyancy force minus the weight of the balloon. So it is 1,385 Newton. Based on the Newton's second law of motion, the acceleration at the release of ropes is given as A equaling to the net force divided by the mass of the balloon. So we got 2.77 meters per second squared. This is the acceleration when the ropes are released. For the second question, when the balloon reaches the maximum altitude, where the buoyant force B1 would be same as the weight of the balloon at 500 kilograms or 4,905 Newton. Since the buoyancy B1 would be given by this formula, the balloon's volume is assumed same, and rho 1 is the air density at the maximum height. So it is given by the buoyancy divided by GV. So the density would be 0.955 kg cubic meter. Then we can use the expression of the air density given as this. We already know rho 1, so we can calculate Z1 given as this. And the maximum height of the balloon can reach is 2,518.8 meters.